Good morning, everyone, and those of you joining us online now, and those of you who would be watching this lecture as part of our MOOC series on critical raw materials exploration, extraction, and mining. And today I have the pleasure of having Pietari from a structural geology company, formerly at the University of Turku, I believe. And Pietari would take us into approaches for acquisition analysis of structural data from field observation to drill cores. And Pietari, stage is yours.
Okay, thank you, Alireza, and thank you for the invitations and very many greetings. I suppose mentally warm greetings, but physically quite chilly greetings from Turku. I'm sitting in my home at the moment, so that if you hear some weird voices from the rear, we've got in our house the renovation of the heating system, and we didn't have any heating on the last night, and we had -11 centigrade this morning. But luckily indoors we got a couple of plus degrees still, so I'm trying to keep up the pace to keep myself warm. Okay, but let's get started. So the title was Approaches for the Acquisition and Analysis of Structural Data from the Field and Drill Core. And like Alireza mentioned, so I used to work at the University of Turku for some 10 years and in some other universities prior to that. And for the last 2 years, I've been working in a company called the Structural Geology Company in structural geological consulting. And many of the experiences come, I suppose, from the both periods of time. And let's go on. So in essence, what I'm going to be talking about is could be titled under two or placed under two titles. The first would be approaches, so in a way, why, and the other one is methods, and that would be answering the question how. And let's go into these. In here, I listed according, or in my opinion, 5 of the most sort of essential and most important approaches. And the first would be in structural geological work, in particular related to the drill core logging, but also other would be accumulate understanding and not data, and maybe an addition, not only data. Since a lot of data will actually not help you if it is not representative. So first we are going to be walking through these texts and slogans, if you like to say it so, and then I will be showing some examples afterwards. The next one, which is in the heart of the structural analysis, is recognize systematics and patterns. Proceed from that into delineation domains that are internally homogeneous or homogeneous enough, and then eventually recognize deviations from the patterns. And in a way, the recognizing the deviation requires that first you need to understand something sort of which is common for most parts of your area. For example, you have to make understanding of the systematics, and then you can go into recognizing the deviations. And in a way, that's typically when the fun begins, and many of the important things are associated with these deviations from the pattern. And also, this way you can make understanding of some initially typically quite chaotic data sets, in particular if dealing with the large data sets. There's going to be a lot of noise in all the directions, and it requires that you work systematically. Make the most out of the existing data sets. This is sort of what happened during the last couple of, maybe last decade in particular. Maybe one good point in here would be to refer to the LiDAR images of the land surface and the morphology, and that can be linked quite in many cases back to the composition and structure of the quaternary deposits, and then the bedrock even, which is underlying the deposits. And therefore we need to use an approach where we first make most of the already existing data sets before we go and do any work on our own, in a way pre-field or pre-logging analysis. And that will be providing improved focus and efficiency for the field work. And work systematically, one topic at a time. start with independent data-specific analysis and later on continue towards correlations and data integration. And there, in a way, typically, in many cases, many or sort of all things are related to each another, but then you can't really tackle everything by going in a one go, in a way. You have to do it in like incremental steps. Communicate effectively. I think this is one important thing when you come and wherever you communicate to your peers or to anybody else. So you need to try to be very effective and focus on the known features, the results, and not really so much on the unknowns. Well, the uncertainties need to be communicated as well, but don't focus on the unknowns, but start with the known features, and then towards the end you also need to introduce those things that are not known. And I would state that the poor communication can lead to valuable work being wasted. But let's go into the first example. So, and this relates to the accumulate understanding and not only data. In the stereogram here, in the low hemisphere projection, we got foliation, poles to foliation in here, and the density of these poles. And you can see from the N number here, there is more than 3,700 foliation measurements included in this plot. And then the next one, a bit smaller number, but still 2,100, and that has to do with the bedding. And at the first sight, these appear to be very similar. But actually, if we go on and highlight some of the clusterings in the stereograms, we can see that, well, the black area in here is roughly the same as the area covered by the more dense foliation area here in the left-hand side stereogram. But if we look more detailed into the bedding, so we actually see that there is sort of an elongated tail in here towards the bottom of the plot. And recalling that the total number of the observations is large, more than 2,000. So it means that even in this less dense area, there are very many hits, so to say. And if we would like to look at this, what it actually means when we look at, for example, a map, so that this area shown by the orientation population shown by the angle or arrow, how that would be looking on the map. So actually, this sort of form line map, I will be telling later on what the form lines, what they are and why they are useful. So where these actually do locate. So these individual measurements shown by the red dashed line actually are defining the hinge area of the asymmetric folded system. It means also the density in the plot that the bulk of the measurements come from the flank of the fold, and then the minority come from the middle, but still they are actually covering a large area. So that thereby, if you only add the data, you don't get the idea of it. So you need to accumulate understanding. Going to the next example in the same topic, that's an area in on the Gulf of Finland, southeast of Helsinki. A couple of skerries, couple of 100 meters across, and the gray areas have been imaged by the drones, and the fraction traces are the purple lines, and the thicker lines are the faults. So sort of a lot of chaos in a way, and a lot of things, and like a big data set, and where to focus. And in that particular case, the guideline would be that check at the position where you are positioned with respect to the fault. And here the faults are the red traces. And then when we put the red traces for the fault slip planes on the map, then we can actually start recognizing different fracture patterns around it. The regional one is orthogonal to orthogonal fractures, but actually then in the tips of the fault, we've got a specific fracture pattern deviating from the regional background orientations. There are some step overs. There are some areas of interaction between two different faults. So we need to understand where we are in order to be able to focus our research efforts. Then there is also a lot of variation in nature and many sort of different targets, and one might be tempted to do some averaging and generalization. And this is like these two slides are now an example of what actually could you generalize and what should you and what you shouldn't. So for example, this is an intrusive body and one drill hole has been placed through it. So the question in here could be that would it be acceptable to estimate an average foliation for each 1 to 2 meter interval? So if the foliation shown by the blue lines here is a bit fluctuating around the vertical. And the answer to that would be that yes, most cases that should work, since this will sort of result in a representation of the dominant foliation within the intrusion. But it also has to do with the focus of the work. It may be that more detailed observations should be conducted close to the contact of the intrusion, since then we might get an understanding on the relationship of the deformation with the host rock and the intrusion, or for example, the emplacement mechanism of the intrusive body itself. Another quite contrasting example would be that the question in here is that what about averaging the bedding data for metasedimentary rocks? And in that case, they would be like in the previous example, they could be close to the vertical orientation, fluctuating a bit on both sides. And then an addition, what has sedimentary younging or way up to do with the question, or does it? So here we got a drill core piece with very nice graded beds and load casts pointing that the way up or stratigraphic younging is upwards. And putting this image, it's quite a similar box cartoon in a way like in the previous example of the intrusive body, but in here we got folded primary bedding shown by the gray lines, and in the big picture everyone by these black symbols are actually pointing the opposite way in different parts of the area, and thereby it means that actually it must be folded, and we see the folding pattern here in the cross-sectional view. And that also means that taking average values for bedding in the drill hole in here, let's say between at 1 to 5 meter intervals, that would lead to failure in recognizing the folding in the first place. So it's up to the situation as well. What is our geology about? How much can we, for example, average? And if we can average or if we can't do any average. And another example of accumulating understanding, this would be quite relevant for exploration. And this is like a sketch image sliced into a couple of bits and pieces. And it could be also entitled that how to trace the mineralization into the unknown subsurface. And in this, on the right-hand side, we can follow these steps in the discovery, and the numbering going from 1 to 6, I remember, is shown by these numbers, which are highlighted with the green in the drawn sketch image. And we see it's a cross-sectional view. We see the house on the top, and that's the ground surface up there. So we start hitting the first intersection in the first drill hole. And from there, we know we get structural information. We get the intersection of the mineralization shown by the red. We get the orientation of the bedding. So we can extend and extrapolate the understanding of the mineralized horizon to start with in a specific orientation from bottom right to the top left in this view. Going on, we make another drill hole to the right hand side from the previous one. So number 1 in here, we get another hit here. So it's relatively at the same elevation in here, and the length of the intersection is approximately the same. But what is deviating is actually the bedding orientation. Now it's dipping the opposite side. And then already in here, this is an example I will be also highlighting later on, that in structural geology, you typically need to sort of work in a way that the work you already did will be in a way guiding the ongoing and future work. So here you can take the bedding orientations from spot 1 and spot 2 and just manually sketch it on a stereogram, and then already you can define the intersection of the great circles will be defining the fold axis orientation for you. Then you get the grip of the geometry of the system already based on just alone 2 different observations. Going on. So now we also realize that, okay, in the backyard of the house, there is actually an outcrop. We go on the door and knock and ask the owner, okay, can we please visit the outcrop? Yes, okay, there, no problem. So we can also see that, well, the bedrock outcrop also shows folding. So this is now confirming our interpretation based on the first 2 drill hole intersections that the geology is folded geology. So it's confirmed with the outcrop observations on the ground surface. We go on in the intersection, in the process, and we make another drill hole. So that would be like a starting from the same position as number 2, but actually drilled into the other direction. And now number 4, we notice that we were expecting to have the mineralization higher up in here, but instead we get a lot of some crazy chaos in here going on, and we can't really hit the mineralization. But instead, actually, we are hitting the mineralization much further down in elevation than what we expected. So, and using that information that the position is unexpected, and we get a lot of structural chaos going on in this part where I'm showing the pointer at the moment, so we can make an interpretation that there is a fault structure. And the last step of this story is that, okay, we can also, maybe now we didn't pay enough attention to the outcrop at the first, we only checked the first round of field mapping, we noted the folding, but then we can look more detailed in that. We also see that along the kinematics, and then we can use this reverse kinematics as a proxy to interpret the fault, the kinematics of the fault that we encountered between the observation spots number 2 and 4. And then in the final part, we make another drill hole here in the far right, and we see that the bedding in the vicinity of the mineralization intersection is much, much more steeply dipping than in any of the previous drill holes. And we recognize that there is actually some shear zone shearing going on, so we must be in the vicinity of the shear zone. So this is just to highlight in a way the process that way how we should go on and do the structural work, that we collect bits and pieces of information from here and there, and then we try to put these pieces of information together and always keep complementing the story and guiding the ongoing work. For example, how should we place the future drill holes, and what are we expecting from them? Okay, something else. We noticed that there was quite a bit of complexity going on in the previous drill hole, and that would be one approach in acquisition of structural data, that in quite many cases you likely are never going to be solving all the complexities in your structural system, but it might be in those cases enough that actually if you can delineate some areas that where things are getting really complex, maybe no need to sort of characterize everything in very detail, just delineate that, okay, here I've got that area that is really complex, and I can try to understand the geology on the both sides of that. And going back to this previous example, we recognized between the targets number 2 here in the left and number 4 in here, there was a lot of chaotic structures along the drilling, and then that could be delineated as an area of structural complexity. Okay, going to some examples about the recognizing the systematics and patterns. delineating domains, and in particular recognizing the deviations from the patterns. Go back to the suitcases in a while. So what are the deviations from the system in here? When we look at this drill hole section, that's a drill hole going in here, some structural line interpretations in here, two different mineralized horizons here in the middle, and then in the bottom right. If you look at these two different hanging walls and then the footwall, at the first glance, all the great circles, almost all, seem to be pointing towards the same orientations. That would indicate that the beddings here, and these are beddings and bands, so they would be dipping quite gently towards northeast. But actually, if we look in more detail, there is one very critical observation that we see this one here on the stereogram in the hanging wall number 2, one in here, and then two further beddings in here. And actually, these occur in a very limited spatial area, just below the upper mineralization in here, and highlighted by the arrow and these shear zones in the cross-section interpretation. So this means this would turn the situation in very different, that if we didn't recognize these three different deviating bedding orientations, we would consider most likely that the mineralization would be actually continuous along the bedding. But now we actually know that it is much more probable that the mineralization has a continuity along the cross-cutting tectonic structure, since it's only a couple of observations that are deviating from the pattern. So individual observations actually can make a really big difference. Another perspective into patterns, that was from the one individual drill hole, but now we are looking at a regional study from the Peräpohja area in northern Finland, so just at the end of the Bothnian Bay, close to the border of Sweden in here, Tornio and Haaparanta over there. And then magnetic map, a lot of different types of known mineralizations, and then the structural setting is of the rifted Archean continent, and now we are just on the supracrustal rocks located on top of the rifted Archean continent. And the aim of the study, now we're going to the suitcase story, is that if you look on the top of the suitcase, we see that, but when you go take a flight, they will make an X-ray scanning of whatever you got inside there. So the purpose of this study was in a way to recognize what we have got on the top, but then also try and see what potential structures might there be in the underlying Archean basement. And sort of the apparent thing, this would be the casing of the suitcase. What we can see is that of the fold and thrust belt signatures. So this is a cross-sectional view down here in the base. We see quite many folds in here, and then on top of the folds, we see this typical rollover anticlines and folding in a bit different character in different geological units. And we actually see also something more. We see the deviations from the fold and thrust belt patterns, and that's where things are getting interesting. So we see a couple of things. For example, here the green arrow tells the Kemi fault zone in here, so it's definitely something that is coming all the way up in here. We get something, we got this doubly plunging anticlines in here, and they are typically making like whalebacks in here, very smooth curvatures, but all of the sudden one is terminating very abruptly here, and another one is also as if that was sort of cut off. And then one further thing is that we got a particular zone here in the middle where all the fabrics are deflected and turned into. There is sort of the smooth structural zone in here in between. And then the question emerged, do we potentially have some basement involvement? So whatever we can see on the map directly is anything happening in the Paleoproterozoic supracrustal cover sequences, but the basement in this case is the rigid Archean rifted continent. Can we recognize anything from there? And that was our interpretation of the same area. So this area in here is covered by the Proterozoic rock, but these structural features were interpreted based on the gravity data now visible in here, and then using the structural sort of deviations presented in the previous slide. And thereby we could tell that, yes, we could see inside the suitcase, at least to some extent. Going into topic number 3, so that would be make the most out of the existing data sets and also, of course, work systematically. So, for example, this is just a snapshot of one GIS project from QGIS, like in a way, table of contents. So, telling that there are many elements that you actually need to work with many stuff before you go into the field. So you got maybe some existing line interpretations, existing point data, you might have drill holes available, and then you might have some like geophysical data before you go into the field, and based on that, you need to do the work before you go in the field, since that will be then guiding the ongoing work in the field. And that's going to be, you can focus your fieldwork efforts, that it's not sort of out of the black in a way, but you get an idea and hypothesis for each particular area before you go in the field. And then this is also something that could be highlighted in here, that I will be going into the form lines, like I mentioned. So this is from one project we conducted. So the many sort of layers of the form lines, and that requires that you have an idea why you do it, and you get a system and you can categorize things. So for example, form lines could be conducted before the field work based on the existing geophysics, and you could put those in different categories like continuous banding, discontinuities, and if you get like massive, very high magnetic signature units, those could be like polygon objects. Field geology form lines, that would be, of course, naturally something you do after you have been in the field and collected your point data. And that goes hand in hand with the properties of your geological area. If it's got layered rocks, you need to incorporate bedding, typically foliation. You got faults, shear zones, axial surfaces, etc. Might be veins and fractures as well. You may have some drill holes material, drill hole data in the area, and from the topmost parts of the drillings, you could also make another layer of form line interpretations, and that could have the same elements, like S0 is typically the bedding, like from the field data in here. And you could have the lighter form lines also from the digital elevation models, just like elongated ridges or the topographic depressions, and that would be one element. You could also add something in here if you got existing older geological maps, for example. You could go and make an interpretation out of those as well, and then you go and work with many different layers of data and interpretations. This goes also, I think, hand in hand, that you should work systematically one topic at a time. An example would be something that can be done quite nicely on the drill hole data. And typically you work with many drill holes. Sometimes they are arranged in elongated or continuous sections, sometimes in a more chaotic geometrical arrangement. But nevertheless, so we consider the situation 1 in here. We got a section with 2 individual drill holes. We can define some intersections of particular structure, shear zone or fault, for example, in here, another one in here. So we first need to look at one hole at a time, then another, and only thereafter we can go into something called cross-hole correlation in this context. And that would then require having the intersections, but typically also some orientation data, maybe some geophysical data or hydrogeological data to support the continuity of the feature. And only thereafter you can actually go in and do the 3D modeling of the deformation zones. And that would be an example of the single hole interpretation that can use fracture frequency, rock type, alteration, etc., or many different properties. Like this is a bit wider set of properties where the interpretation has been relying on different rock quality classifications, RQD, a Q class, and the Q parameters, joint alteration, joint roughness, joint set numbers. This is the fractures per meter, these gray bars in here, cumulative fracture frequency, different orientations for the fracture properties, and even some point load tests on the rock mechanical behavior of the particular spot. And based on that, these single hole interpretations of different intervals of interest can be defined. Another data set regarding the drill holes, there is point data and then interval data. And something that might be very useful in doing the logging is the interval logging. And here, for example, there is meters from and meters to along the drill hole. And you could make quite rough and rapid, quick and dirty, so to say, assessment of the intensity of foliation, intensity of veining, so how much veins there are in a particular interval, and then, for example, the fractures. And you can make a heat map and compare these particular issues together, how they would be fitting. So in this particular case, it would appear to be that the foliation and the fracturing, they go hand in hand, roughly at the same depths and intervals. And the vein intensity is always preceding the intense foliation and fracturing. So you start recognizing patterns that otherwise may be left unnoticed when you work in a way very systematically and as objectively as possible. Another example of the foliation intensity data. So it can be very sketch-like and schematic to start with. I will be highlighting the importance also of sketching a tiny bit later in here. This is one drill hole trace, couple of mineralized intersections, and by the density of the drawn lines in here, the person who did the sketching in here has been able to demonstrate that it's the top part of the mineralized intersection in here, or the R zone, that definitely has experienced the highest ductile strain. So the intensity of foliation is the strongest. And furthermore, an inset shows that there is even some shearing and like relative displacements between the blocks, and in this case that would be south block up movement. And of course you can develop and elaborate these sort of early sketches and combine it with the heat map logging, interval logging shown in the previous slide, and make like a really complete description of the drill hole. In here, the foliation intensity from very light gray to the black is on the left side. We see the black is here, where there is the shearing symbol as well, and then another shear zone and intense foliation in the vicinity. And the vein intensity is on the right-hand side, and that's not, in this case, not fully following the foliation intensity. And the lithology is in the middle. Okay, one last point about these approaches is to communicate effectively. I put so the question, but you are not able to maybe answer at the very moment, but something to think about is maybe that, have you heard something about the flame geology or flame tectonics? And if you are interested, I actually posted a little talk in the LinkedIn, and the link is here on the bottom right. So that had to do with the flame geology. So that in the Finnish geological communication, it was quite common that sort of like the contacts here on the geological map, they are really like flame-like. So it's in a way the measure of uncertainty. You really don't know what's going on. In a way, you can introduce these wavy flames, and they are sort of communicating. It's somewhere there. It's maybe don't exactly know how it's oriented. Don't know exactly what's the character of that. But in a way, many times the communication in, at least when I did study in Finland, was started with the uncertainties, and in a way, then the engineers later on always told that, yeah, okay, it's going to be some flame geology once again. So that would be sort of the good lesson to learn, that start communicating with those things you know, and then go on explaining what are the things that can be known and what can't be known, and associated uncertainties. Like in here, we got lithological units A, B, and C, and it may eventually be, if, for example, in this particular example, if we are communicating with the engineers, it might be, it potentially doesn't have any significance if the things that are being constructed or will be constructed are cited in lithology A, B, or C, but it might be much more important to have an understanding of the structural orientation of the system, since likely that is going to be controlling a lot of the fracturing orientations and fracturing properties. But go ahead and give it a read if you like. The link is over there, down on the right-hand side. Okay, so going to the second half, this is a shorter one. So the methods, and those would be sketch, be bold, don't hesitate, make mistakes, revise. And sketching, I think, is needed both to document and to interpret. Also to sketch, to develop the conceptualizations and hypotheses. Use form lines, I will show examples. Use maps, sections, and spherical projections or stereograms, like typically referred to. Use separately, but particularly all three together. And think when you work. When I was at the university, some bright young lady told that, yeah, have your brain turned on. I think that's a good tip in doing any geological work, but in particular the structural geological work, since you need to be guiding your work with the understanding you already have. Just an example of the sketch and the field photo. Quite typically some dirty rocks, some shadows, a bit poor perspective, etc. So it's very good to make a sketch, since then you need to sort of think through what you have at your hand, what are your important elements. Here, for example, we got the symmetric open folding, we got some quartz veining in an echelon pattern in a particular zone, and we got the cross-cutting foliation. We got many structural elements shown in here. We can also put the P1 and P2, P3. We can localize our field photographs, detailed photos. So we got a like coherent, watertight documentation of our stuff. Also sketch to interpret an example from the seismic data, like the top left is an unannotated one, and then a couple of different versions of the annotated ones. So in a way, and the good practice in many situations is to have a blank field image and then an annotated one on the side. So you can, everybody who is looking at the stuff afterwards, they can make their own opinion about the unannotated image, and then they can compare with the annotated and interpreted one. And eventually any geological map, in particular the structural geological map, that's in a way always a more elaborated sketch in a way, since there are always unknown features in here. We didn't have data from each individual spot. In here, for example, you can definitely see there is no data, just the lines are continued. But anyways, it's a way, when you keep sketching, when you do the field work, when you plan the field work, you got an idea already. And in a way, you got a mini map, you got pieces of the mini maps, and you can eventually put these pieces together and make a complete map. Form lines, one of my favorite things. So that's a powerful tool in visualizing and analyzing the structural patterns. And you can highlight it, for example, just have the intrusions and the host rock, and then you can quite nicely see the trends. What's going on? Two intrusions, intrusive bodies in the middle, some high strain zones, and then the geological trends of the foliation in the west are quite different from those in the east, in the example in here. And that was the example I showed previously. There typically needs to be very many layers of different form lines. It's up to the purpose of the work, of course, as well. And what the form lines actually then are, it's in a way to generalize something, individual point observations, and make a continuous interpretation out of those. So in this example, we got 4 different outcrops, 4 different structural measurements. So that might be a try to go and how to make a lithological map from the lithological data alone. Just make the stripes in here and the colorings will fit the outcrop information. But actually, you shouldn't go that way, you should go this way. First, make use of the structural information from your outcrops and make a framework, geometrical framework for your geological interpretation, and then eventually fill the surface of the map with the colors. So that would be correct, and that one will be incorrect. This is also a good way to find patterns. And when going in the field, you might, in a typical case, have isolated little patches here and there outcropping, and then something covered in between. And the typical approach in doing the geological mapping would be try to cover as much of the area as you can, in particular at right angles to your axial surfaces in here. And the examples will show the difference between 2 hypothetical cases. So the green lines are the bedding and the dashed blue are the foliation along the axial surfaces. So in case A, we got the system 4 outcrops. We can define an enveloping surface. So in a way, the surface that is capturing or sort of enveloping the package of rock in between. And then the axial surface in this case is roughly at 90-degree angle. But if we go on and extend the mapping a little bit, build some more moss, for example, in the forested areas in Finland and Sweden, so we can observe another outcrop in the east, another outcrop in the west. So that will actually change the situation a little bit, since now in this case, our enveloping surface of the structure would be at quite different orientation to the previous one. And then the relationship of the enveloping surface and the axial surface is not anymore 90 degrees, it's quite a lot less. And then comparing the 2 cases, so in the case A, actually, it appears that we would be in the hinge area of the folded structure, whereas in the B situation, we would be on the limb, so on the other flank or the other side of the fold. So it's in a way quite a big game changer. Approaching the final slides, I think, so that would be, I think, one thing I learned when I did a lot of teaching in structural geology was that many people claim that, okay, I don't have this and that 3D thinking in me, I can never do this. But I think that you need to have a system, you need to have a framework where you can implement your research. And in structural geology, I think you should always make your best effort in combining the map here on the left, the cross-section in here in the bottom, and then the stereogram here on the top right. And the the green lines are the beddings from 3 different outcrops in here. We see that they are dipping. Actually, these are dipping the wrong way around. They should be dipping that way. Sorry for that. And then here is a great circle representing the same dip of the bedding surfaces, which are dipping some 70 degrees to the northwest. Since the other option would be that you work only in 3D, and then your things get normally quite difficult to handle. Everything is related to everything in a way, but you need to work in steps and stages. Map maybe from the surface, maybe from different elevation levels if you are working with 3D data sets, with drillings of 3D geophysics, geophysical sections. Make a cross-section at the suited angle, in this case from the Kristineberg in Skellefteå district, Sweden. There is sort of the dogleg cross-section in a way, or the 3D model. And then there is one section in here, it makes a little corner. And the purpose of the corner in here is that it allows to sort of look at an optimal angle to the structure. So the section in here is at right angles to the fold axial surfaces, and then in here it's the same, since the axial surface orientation is different in different parts of the area. But I mean, if you got trouble in sort of figuring how things are in 3D, make it in steps. Do the map, do the section, do the plot, and eventually, I guarantee you will learn. Okay, finally, so think when you work, and work in a way that the conducted work guides the ongoing and future work. And I think this should be done in a time perspective, starting from a couple of minutes all the way to the field season and beyond. And I think this is particularly important for structural geology, since if we imagine this example of the form lines, so we normally start somewhere, we get some idea, we can cover a bit and piece of the mapping area, and then if we visit this outcrop first, and then we visit this one in here, without further thinking, we don't really know where to focus. Maybe we go in here, maybe we just then walk along the forest road in here and are getting hungry and are heading to the lunch. But actually, when we realize that, okay, this thing is dipping to the right or to the east, and the bedding in here is dipping the opposite way, that would, a bell should be ringing in our head that, okay, we actually crossed a fold hinge, and then we should put any future effort in between the outcrops and not on the sides. So that would be sort of the thing. And if we can't cover this, we can't figure out that we should work in here, we sort of lose the opportunity if we don't work while we are already doing the work. If we only collect the data from here, from there, and then we go into the office and leave the field area, so we might be sort of realizing it way too late. Another example in here might have been that, okay, we realized that a lot of things are actually happening here within the top part of the ore zone, and we should place a lot more effort in actually tackling the kinematics as well, if available, from that particular area. So we don't need to cover all the pieces of the drill hole at 2 meter intervals, like even intervals, but we can make just a couple of spots in here and also down in here. Nothing so interesting is happening, but we should invest a lot of effort in the area where we actually got potentially the possibility to solve the problems. So, to sort of wrap up and repeat, so, and thank you and leave room for questions, I would like to repeat sort of what we walked through was the approaches and methods, and repeat as well. So the approaches was accumulate understanding, not only data, recognize systematics and patterns, and in particular the deviations from these patterns. But to be able to recognize the deviations, you need to be able to systematically work to find out the patterns first. make most out of the existing data, work very systematically, invest time, for example, in organizing your 3D model where your data is located, and so that you can also find it from your folders on your hard drive or OneDrive or whatever you use. Communicate effectively to the public, but also to your peers. Sketch and be bold and sketch, and use the thin pen first and make it thicker if you go wrong. Use form lines. Definitely you learn these and think through sketching. I think that's really like a connection between the hand and the brain is really like something you can't skip. Use maps, sections, and spherical projections. It's a powerful set of 3 methods. And think when you work. So that's all from my side.
Thank you, Pietari. Very fantastic lecture. I think I must say that I myself now a bit feeling better. When I see all the structured geological maps and the work of yours and others, I get panicked. But I really appreciated that you showed today that you could do this by going step by step. So
okay.
Thank you, Pietari.